Okay, so let's talk about fluids, static fluids, and specifically what we're interested in here is um, pressure and force. Okay, now the way pressure works underwater is that the pressure at any given depth is equal to rho times g times the depth that you're at. Okay, so z is measured from the top down like this. So it'll be upside down. Okay, but that makes more sense if you think about it as depth. Rho is the density of the liquid, okay, which is going to be water most of the time. And then g, of course, is the acceleration due to gravity. Okay, now let's take a quick look at our units here. So rho is going to be something like kilograms per meter cubed. Okay, and g is going to be meters per second squared, and z is just going to be meters. Okay, and so what you can see happens here is if we rearrange this, okay, this combination here, kilogram meters per second, that's a Newton. And then I've got a meter over a meter cubed, which is over a meter squared, okay? So that's a Pascal. Okay, that's how that all works out with our units. All right. Now, your book often has this value, okay, which it calls the specific weight instead of the density. All right. Now, how that works out is like this. So see how it's pounds per cubic meter? All right. So that means really we could write it P as gamma Z. Okay, now let's look at those units. That's going to be pounds per cubic foot, and it will be in English units, so that'll be underwater as feet. Okay, and so then you can see we're left with uh, we're left with pounds per square foot. Although apparently I can't write that. All right. It's been a long semester. Just like that. Then, if we needed to, we could convert that to PSI or to atmospheres or whatever we wanted to do then. Okay. So that'd be pretty easy to do. All right. So these are our principal ideas right here. Okay. Boom, 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 boom. All right. Now, let me erase some of this other stuff here. Get rid of all this messy stuff about units. We don't need that right now. Okay, so what we've got here then in this particular case is it's wanting to know the magnitude of the hydrostatic force on the gate AB. Now the gate AB is this thing right down here. Okay, and I don't know who decided to put a gate at the bottom of the swimming pool, but somebody did. Anyway, so what we want to know is what's the force on that thing, okay? And so we're going to be interested in the total amount of force headed downward on this thing like so, okay? So we have a couple of ways to do this. I'm going to show you both because it's instructive to see both ways to do it. The first way we're going to do it is just to straight up use the pressure, okay? And so the pressure depends on our depth. And our gate here is all at the same depth of 4 feet. Okay. And so we could say, I'm going to do it like this. I'm going to say the pressure at the bottom is going to be rho. Well, we don't need that because we got gamma. Is gamma times the depth. So I'm going to put ZB for the bottom, just like that. Okay. And then if I wanted to convert that to a force, the force there at the bottom of that thing is going to be the area at the bottom times the pressure at the bottom. Okay, so what we're really looking at then is the area there. It tells us it's 3 feet wide. Okay, and then up here, see where it says it has a width of 4 feet. So what's hard to see is that it goes into the page, okay, into your screen. All right. So it's 3 feet this way and 4 feet coming into your screen like that. So our area then is going to turn out to be 4 feet, or sorry, 3 feet by 4 feet. And then our PB is gamma ZB, and gamma is 64.2. Oh, no, I had it right the first time. 62.4. All right, and that's pounds per cubic foot. And we're down there at a depth of 4 feet. Okay. All right, now let's look at the units. Okay, I got feet, foot cubed. Cancels that guy right there. So all we're left with then is pounds. All right. And if we run those numbers, which I did already, what we're going to get is 29.95. Okay. And that's pounds. Okay. Now, so that's just sort of straightforward using the pressure. Here's the other way that we can work this. All right. So let me erase some of this stuff along here. Okay. The other way to work this is just to say, oh, look, I got a chunk of water here that has a certain mass. And so the force down here is just going to be the weight, M times G. Okay, so let's think about it that way. My weight, which is going to be my force there at the bottom, it's mg, which is going to be my density times my volume times g. Rearrange just a little bit, we get rho gv. Okay, and rho g is just my gamma, so I got gamma times v. Okay, so let's go ahead and put the numbers in on that. So we got 62.4 pounds per cubic foot. All right, and then what are we going to have for my volume? Oh, well, look at this. It's 3 feet wide and 4 feet back into the screen and 4 feet tall. So I got 3 by 4 by 4, which is exactly what we had over here. 3 by 4 by 4. Okay. And so we're going to end up getting exactly the same thing, of course. Okay. Just like that. Now, sometimes for our situations, it's going to work really well to come at a problem from this angle. All right. That's the most flexible way to do it. And other times it's going to work fine to do it this way, to think about it like a whole chunk. Okay. And so we can do that. We can do that too. All right. So we got 2 ways to go about this. All right. So the next problem we're going to look at is one where the window's on the side. Okay. And when the window is on the side, then we got to think about the pressure a little more carefully. Okay. Because it's going to have different depths to it. All right. So close this one out.